kind of piggybacking off of the theme that Barb introduced with off-the-shelf approach to marine surveillance, I wanted to share with you a project that we recently started at NASA Ames called the FrankenEye UAS project. And most of us in the room are familiar with the story of Frankenstein, where a scientist takes human body parts and then creates a new monster from those parts. We've taken a similar approach to UAV design, kind of with this thought process in mind. We can use a building blocks approach for achieving new UAVs that have enhanced performance capabilities and the ability to carry more sensors and fly for longer duration. This project builds on two core competencies that we have at NASA Ames, one of which is the Intelligent Systems Division, and this is really the division that focuses on adaptive control laws for UAVs and for spacecraft as well. There's also a lot of work in autonomy and neural networks along those lines. The other research theme that we have at NASA Ames is Earth science, and so we operate UAVs that will have planned missions to a volcano or to a hurricane or to parts of the Arctic to build a better understanding of our environment. And so this project is really a kind of a merger of ideas from those two core competencies that we have at Ames to build UAVs that can be used for science missions, but can also be platforms to be used for other applications such as marine surveillance. So in 2013, NASA Ames was given several surplus UAVs that were originally operated by the U.S. Marines, and they were originally used by the soldiers as kind of a hand-launched UAV that could be used for getting information about what is happening over the hill and used for decision-making on the battlefield. When we received these UAVs, we determined very quickly that they were designed for a purpose other than science missions. Their endurance is about an hour, and they're designed to break apart very easily. They're designed to be marine-proof, as they say. But for the science missions that we had in mind, we really needed to focus on extending the endurance and extending the ability for these UAVs to carry sensors that were important to our science missions. So what we did was we started with the basic UAV and kind of outlined the properties that we could expand upon. The wing designed for this UAV is rectangular, which makes it very easy to build off of. And we also put in some time to understand the characteristics of the wing and the airfoil design. It seemed to be a design that we could improve upon. So we took an approach, which is kind of summarized in this chart. We wanted to first show that we could extend the flight time capability of this aircraft by increasing the flight time by 20%. And this was simply a project focused on adding wingtip devices to the wing to provide it with a higher aerodynamic efficiency, which would give us a longer flight time. And the other objective that we had was to increase the payload capacity of this aircraft for carrying sensors and other things that are of interest to science missions. And so this project really focused on span loading the aircraft by attaching multiple aircraft end to end to form a large wing, which should, in theory, be more efficient than a smaller span wing. But we saw also that as we were expanding the capabilities of this UAV for science missions, there seemed to be some overlap with some of the interests for marine protected environments and interest in surveillance of those environments. So we also outlined a list of requirements that could possibly be met for the purposes of marine surveillance. And these are some of the list of requirements that we had for a UAV that we're currently developing. The main requirement that we were working towards was how to achieve a 10-hour endurance from an aircraft that costs less than $50,000 to build. And we think that we have the key ingredients that are required to do that. In fact, we have a demo aircraft, but we're still planning our first flight for that aircraft. Another thing was we wanted to show that this airplane was modular enough to be transported inside of a small car or possibly even launched by one person, assembled by one person as well. And we think that this design, by building on top of the DragonEye UAV design, we can also meet that requirement. there are a number of challenges that we see as we're expanding the capabilities of this UAV. One of them is a manufacturing challenge. As you attach more aircraft together end-to-end, the strength of the wing is very important for maintaining the stability of the wing and of maintaining the flight characteristics. And so we saw an opportunity to use rapid prototyping methods, such as 3D printing and laser cutting, to build in the strength requirements for the wing to allow us to achieve the endurance requirements and the payload requirements. These are some of the methods that we're going to be investigating over the summer through a student competition, which is officially going to be sponsored through NASA. The student competition will bring in students from different backgrounds that are relevant to what we're doing, and at the beginning of the summer, we'll provide them with a library of parts for this aircraft that can be 3D printed or laser cutted, or laser cut, or manufactured using some other technique. And then we ask them to go and build their own aircraft that can satisfy emission requirements. And we expect that fused deposition modeling will be used on the 3D printing side for manufacturing some of the parts, the wing sections, the nose cones that are required for sensors. We also expect that there's going to be some interest in laser sintering, which has been used before in some UAV applications, one of which is shown here. We also want to explore opportunities that might present themselves in building molds instead of the actual part for a component that's going to go in the UAV. The idea of building a mold is that you can then use vacuum bagging techniques to create a carbon fiber piece from the mold or a fiberglass piece from the mold with the reduction in time to manufacture that mold piece. And then another concept that we're looking into is a concept called electroplating, where you can take an inexpensive piece that you 3D printed out of ABS plastic, and then you can coat it with a stronger material to improve the strength properties, the bending properties of that material. It's also been used very heavily in the automobile industry for mock-ups and things of that nature. Another core competency that we're trying to build at Ames, and that we actually have several tools in development toward expanding this capability, is in an area called aeropropulsive elasticity. So when we think of aeroelasticity, we think of the interaction between aerodynamics and structures, and this is very important for large wings that you might see on a UAV. But one of the considerations that is often overlooked is the effect of the propulsion on the structures and on the aerodynamics. Just to give a very quick example, by providing some thrust input to a motor that's powering a fan, that fan can then twist the wing, and that changes the aerodynamic properties of the wing. So we have a core competency that we're developing in modeling the interactions, these complex interactions that are required to understand how to extend the endurance capabilities of these UAVs for science missions and for marine surveillance. We'll be developing these capabilities over the summer again through a student UAV competition. We're always interested in partnerships that would help us to enhance the capabilities that we're going to be demonstrating. We also have a fixed budget for this project, and currently it seems insufficient for the bigger dreams that we have for expanding this concept. So we're always interested in partnerships that might help us to realize these technologies in the near term and perhaps apply them to marine surveillance applications. So with that, I'll ask for questions. So this is a good question. So what we anticipate is that by reusing an existing UAV, essentially recycling that UAV, most of the cost in manufacturing this UAV is in the labor cost. And so to give you a rough estimate, we expect that these UAVs will eventually be produced in less than a week. So it really comes down to how many people are required in order to build the aircraft, instrument with the avionics that are required for flight testing, and then fly it. And we think that can be done in less than a week. Our target is $50,000, but it could possibly be less than that, possibly be more.
Kevin, were you suggesting at the end there that you were thinking of taking advantage of a property that animals always take advantage of, elastic energy storage to increase endurance?
That is one of the areas that we're exploring. It turns out that in some of our recent research projects, we've shown that birds have, well, using birds as kind of an example of efficient flight, birds get a lot of their efficiency from the flexibility of their wing, and this is kind of counter to the traditional way of thinking about how aircraft wings are manufactured. Large companies, they want to stiffen the wing to improve the performance of that wing. We're actually seeing some advantages in softening the wing, and that's one of the things that our tools are helping us to explore, how to exploit the flexibility of the wing to improve efficiency. And we see a lot of potential in that direction.
I talked about with regard to the concept of operations of the FrankenEye for protected areas the long duration, would you be flying it to and from shore, or would you be covered offshore, or is it going to be reporting on board, flying down line of sight? What's the concept?
Well, one of the capabilities that we want to build into this UAV over the summer is the ability for it to be launched by one person from the shore using a vertical takeoff. We think that we can achieve that by by redesigning the color for vertical takeoff to meet the vertical takeoff requirements. We kind of envision that you could take this UAV, break it apart into its components, which are actually held together using bungee cords. Actually, you break it down into something that can be transported in a small car, driven to the shore, launched by one person, and then 5 to 10 hours. And we think that that's going to be pretty radical, and we think that there's a lot of potential there. We also think that by building into this UAV the capability to do vertical takeoff, it could potentially land on a ship, for instance, and instead of having to return to the shoreline where it would be recovered.
So for surveillance, is the data be coming down to line of sight receivers so that there's not a latency aspect of the data, or would it be just recorded on board for a characteristic?
Yeah, so that's a good question. One of the things that we're really trying to take advantage of in the design of this UAV is the redundancy in the antennas so each of the tails on this FrankenEye has an antenna, and we can take advantage of the redundancy in case the communication is broken through one of the flight computers. We think that, well, by building in redundancy, we can kind of potentially address some of those issues, but if, say for instance, we lost the ability to communicate with the outside world, we could also share this information with another UAV or with something else that's flying at it. We think, I think this is still an area that we need to explore further, and we're always interested in collaborating. Any more questions?
Just an observation. You mentioned evidence good enough to stand up in court. Presumably, since you can envision this, it will be at some point possible to instrument levels of the ocean around the world where we have these types of systems that are taking pictures of ships that are doing things that are inappropriate. So that places a challenge on the rest of us to figure out what data is needed to stand up in court. But I mean, I live in England. They don't have police in every corner, but they got cameras in every corner. And if people speed, they get a ticket in the mail, and they can expect it, and the consequence, people don't speed. So having these systems in the air would be a sufficient deterrent.
Yes, I agree. And we've also given some thought to how to improve, how to validate whether a ship is violating some rule, or whether they're just out fishing or something. We've given some thought to that in terms of how the airplane would operate if it identifies a potential target. It may be the case that we can build into the flight control system the ability to take a different maneuver, or maybe fly closer to the ground to get a better resolution of what's going on. But again, these are ideas, and we think that there's huge potential for expanding that.